Okay, so we have another projectile example problem. This one we have Mr. Craig, a physics teacher at our school, who is a coach for the soccer team at Mission Hills. He's a giant trader. And in this problem, he's helping their best kicker kick the ball. Hours of practice, they kick it at a 30-degree angle at 10 meters per second. The question is, how far does the ball fly? And is Mr. Craig a trader? Let me just answer that second one real fast. This is a big yes. He is a trader. But let's go through the rest of the physics problem, or the physics part of the problem, as opposed to the loyalty problem that Mr. Craig has, and let's start answering it. So we have our little soccer ball. Our soccer ball is going to be kicked at this 30-degree angle, and it has an initial velocity of 10 meters per second. Remember that it also has an acceleration downwards of g, and it's gonna fly as a projectile. That's not a very good parabola, but it's gonna fly as a parabola until it gets some distance x from where it started, and that x is what we're going to be trying to solve for. I want to talk about real fast though this diagonal velocity vector that we have. We can't do diagonals in AP Physics. In fact, in my classroom, I have a poster that says we don't do diagonals. So we're not going to do diagonals. That 10 isn't going to work for us. Instead, we're going to use some of the trig that we've talked about a couple times. We're going to break this 10 meters per second into horizontal and vertical vectors. So the horizontal vector is along this side. The vertical is along this side. Here we have our angle, theta there. And if you remember from the past video, since this is the opposite side, we'll use sine for it. And we can find out that, we'll just write this as 10 sine theta is the magnitude of that vector, the vertical vector. And then the horizontal side is adjacent to my angle. That becomes 10 cosine theta, or 30. I just didn't go that far. I guess what I really wanted to write in here was v sine theta as kind of a generic form, and v cosine theta as a generic form for that one. But anyways, so we now know the horizontal and vertical velocities. And I put that in the sketch area because breaking those up is kind of a drawing type thing, and we're going to need it in our symbol area that's coming up. So anytime you see a velocity that's at an angle, or really anything that's at an angle, you almost immediately need to go to this step here, where you draw it as a triangle and you figure out what the horizontal and vertical components of that velocity are. So going down my list of symbols now, my initial height, I need to set up a coordinate system. Whoops. My coordinate system is, I'm going to put right here as my 0. And once again, I'll do horizontal as positive, like going to the right as positive, and then I'm going to do up as positive this time. In the last problem, I did down as positive. I'll do up this time, and we'll just see that it doesn't change a ton about the problem, and we still get the right answer. So my initial position, based on the coordinate system I just set up, is 0 meters. My final position is the x. That's what we're trying to find out. It's this x right here. My initial velocity, I'm just going to write in v cosine theta. I could write in the exact value, but again, I'm just trying to get in the habit of writing things in as variables. And we'll see that there's actually some nifty tricks that we can do with that if we want to at the end. No acceleration in the horizontal direction. Again, projectiles don't accelerate horizontally. In the y direction, our initial position is 0 meters, and our final is 0 meters. Even though that's not given to us, it's starting at the ground, it's landing on the ground. We know that that has to be 0 and 0, unless the problem says it's being kicked up a hill or down a hill, or it tells us some kind of elevation change. So since this one didn't say anything, it's implying that we're leaving the ground and hitting the ground at the same location. So those are both zeros. My initial velocity in the y direction is going to be v sine theta. And I actually already know my initial velocity or my final velocity. It will be negative v sine theta. Because since this is a parabola, and you guys did this in a problem last week, the velocity at any 2 points along the parabola will be exactly the same. So if it was v sine theta on this part, it's going to be negative v sine theta on the other part. The only thing that happens is it changes the direction in the y, but it doesn't change the magnitudes. And the acceleration for this is going to be negative g. I guess I should have said why this was positive, that's negative. It matches my coordinate system. Initially, my vertical velocity is up, then finally my vertical velocity is down, just like my acceleration is down. So let's start going through and solving it using the same equation as last time, y equals y naught plus b naught t plus 1/2 at squared. This and this both become 0 this time. So I just end up with, if I start plugging in just a minor amount of variables, I end up with v naught t. Actually, I'm gonna substitute in right now the v sine theta. V sine theta. I feel comfortable doing this because I'm not plugging in numbers right now. I'm just plugging in some extra variables. Our problem changed a little bit. This becomes minus 1/2 gt squared. The minus is coming from the fact that we have negative g. So when I've substituted in g here, I had to also make that sign negative. The last problem, since I defined it down as positive, I didn't have to do that, but I did it here. So with that done, I can now add 1/2 gt squared to each side. 1/2 gt squared is added to both sides, equals v sine theta. And then if I solve for t, I'll do the same, basically the same steps I did last time. Multiply both sides by 2, v sine theta, divide, and then divide both sides by g, and then square root both sides. Oh, I'm sorry, no, I don't need to square root both sides. My mistake. Wait, hold on. Because there's supposed to be a t here, and there was supposed to be a t there. My mistake. See, it's supposed to come down. And because of that, that t cancels and one of those t cancels, and I actually don't end up square rooting this at all. I knew that felt wrong when I did it at first. So I could put in 2v sine theta over g for my time. Now I can do my x equation. X equals x naught plus v naught t plus 1/2 at squared. Right away, we know the acceleration is going to cancel because there's no horizontal acceleration, and the initial position is 0 because we defined it that way. So this becomes, once again, x equals v naught t, and now I can substitute in some of the stuff I know. Initial velocity is v cosine theta, and the time from the x equation is 2v sine theta over g. Now at this step, I could just plug in numbers, and it would be fine if I did that, but I actually think math is a little bit neat. So I'm gonna do something cool here. Let's see, the v's become v squareds. Let's divide this by g, and then I have 2 sine theta cosine theta. Well, it turns out that that's 2 sine theta cosine theta. If you remember any of your trig identities, is the same thing as sine 2 theta. So I can actually simplify this to v squared over g times sine 2 theta. That's not an important step. You don't have to do that, but it is just kind of neat that like the way that sometimes these things simplify into like pretty like clean I don't know, solutions. So from there, I can just plug in my numbers. My initial velocity was 10, so that's going to be 10 squared over 10. I did that because it was convenient, times sine of 60 degrees. And sine of 60 degrees is the square root of 3 over 2. And then 10 squared over 10 is 10. So this is going to be 10 times the square root of 3 over 2, which I think comes out to 8.6, something like that, meters. Let me double check and make sure that that is correct. I've got a calculator. Oh, that's right. My son was using it as a phone earlier. All right, let me double check my math real fast, make sure I did that correctly. Sine of 60, yeah, times 10, yeah, it's 8.66. So 8.66 meters. And let me just emphasize how incredibly pathetic that is. The fact that they can only kick it about 8 or 9 meters. I mean, not surprising from Mission Hills, but still very disappointing. So that's how you would approach this kind of problem. Oh, I still have to do the graphs real fast. I'm just going to sketch them in, and hopefully you can make sense out of them. But if you can't, please ask me during office hours or during class. I'll be happy to explain where they came from. For the y, it's going to look like this now, and then like that, and then like that because of my new coordinate system. Actually, I do want to explain this one. Oops, go away. We actually have a full parabola because it's going to start at 0 and end at 0. And then you can see that like right in the middle, it has 0 velocity in the y direction. That's why we're intersecting with the y-axis on our velocity graph. We have a positive slope, even though it's changing at the beginning. So positive that's slowly decreasing at the beginning. And then it starts becoming more and more negative. You can see my velocity graph becomes more and more negative. And this was negative here because we defined downwards as being the negative direction on this problem. So now I want to do one more thing. I'm so sorry. This video is now lasting forever. I want to talk about what changes if we have air resistance. If we have air resistance, there's going to be a slight negative acceleration in the x direction because it's going to be slowing that ball down. And actually, it wouldn't even look like that. This is why it gets really complicated. It would be less and less as it decreased the velocity. But effectively, what that would do is that would mean that the horizontal velocity would start dropping off. And so instead of having a nice line here, we'd have, it would just like, it'd go a little bit less as it went there. And if we got to terminal velocity, it would straighten out right here. And then this would also this would level off. And then the acceleration would fall to 0. And in the vertical direction, again, if air resistance existed, the velocity would drop off a little bit more sharply than we had it dropping off. So it would be a little bit lower, and we would see that it would go a little bit less high and then fall a little bit faster. So that's what air resistance effectively does to projectiles in graphical form. Conceptually is all that you need to understand on that. But at least now I feel like I've covered it